we're going to do the same thing with triple integrals. And if I use a triple integral and the integrand is just the number 1, then we can use that to calculate volumes of solids in 3D space, which is not like, it's not all that useful on its own because we've been doing volumes in 3D space with just double integrals, right? But these triple integrals, if you set up the bounds of the 3 integrals correctly, you can get the volume of a solid in 3D space, and then once you start to work the problem, you'll realize that it's equivalent to doing volumes with double integrals. We'll just do an example. So use a triple integral to find the volume of a region bounded by the plane z equals x, the plane z equals 0, should be the xy plane, and then this parabolic cylinder that's given by the equation x equals 4 minus y squared. So let's graph it first. I got z equals x was my plane. Yeah, and then z equals 0. And then x equals 4 minus y squared. Okay, so that's what I mean by a parabolic cylinder. Is this? It looks like a parabola from the top, but it's a cylinder because it's constant as you move up in the z-axis. And so there's a little region that's bounded between those 2 planes and the parabolic cylinder. Do you see the region, the volume I'm talking about? Okay. Cool, so that's what we're going to try to find the volume of. And we have to choose some order of integration. And we'll call it dx, dy, dz and see if this works. And if it doesn't work, then we can try some other order of integration. So sometimes it's a trial and error process. dz is going to be my outside variable. So I'm going to say that's going to be the constants. And so the minimum constant value for z would be 0 because of that plane. And the maximum constant value for z I could glean from this graph as being 4. If that blue axis is my z-axis, then it looks like the peak of that little solid, it happens at z equals 4. But if I didn't have the graph, then I could plug in, z equals x is the plane that makes the top of my solid. And then also this equation for the parabolic cylinder says x equals 4 minus y squared. So I could say z equals 4 minus y squared at the place where this cylinder intersects the plane. And then I say, well, what value of y gives me the maximum z? That would happen at y equals 0. And so the maximum value of z would be 4. And so then that's going to be the maximum for my z integral, integrating with respect to z. Okay, so then inside of that, I'm integrating with respect to y. And so I have to think, what's the smallest possible value of y? And again, if you had the graph, that makes it really easy. I could look at my graph and I could say, which one is the x and which one's the y? So x is equal to 4. I think the red axis is my x-axis. And so that means the green axis is my y-axis. And that means that y could be anywhere from -2 to +2. Yeah, for that solid. But if I didn't have that, I could use this plane, z equals 0, and find where it intersects the parabolic cylinder. And I already have this equation, so I could just set 0 equals 4 minus y squared, and that's how I could get y is equal to plus or minus 2. So anyways, y is allowed to be anywhere between -2 2 and positive 2, but I don't think it's actually going to be constant, right? If I gave it the constant numbers, then it would sort of give me the rectangular region, but I don't want the rectangular region. This has kind of a silly shape to it. So the values of y I'm allowed to have seem to depend a little bit on the value of z, right? And I'm allowed to make this a function of z because I'm integrating with respect to z last. So these bounds of my middle integral can be a function of z, and I guess I could just rearrange this equation. And actually this would give me y equals plus or minus square root of z minus 4. Did I do that right? Subtract the 4. No, it should be 4 minus z. Oops. Okay, so that means the lower bound on y is going to be negative square root of 4 minus z. And then the upper bound on y is going to be positive square root of 4 minus z. Okay, now x, whenever I place the bounds on what my x variable is allowed to be, I can make x a function of y and z, the way I set this up. Because I'm going to first take the antiderivative with respect to x, and then y, and then z. And so it's cool if these bounds happen to be a function of y and z. Or just y, or just z, if I want to. So again, looking at my graph, if I'm thinking about x, which is the red axis, then it looks like x could be anywhere from 0 to 4 for this solid. But if I just did 0 to 4, it would give me the whole rectangular region, and I don't want the rectangular region. I want this crazy region like this. And it looks like if I make x a function of z, that's pretty good. So if I look at so it's a situation where the lower bound of x is going to be given everywhere by a function of z, right? Because the plane z equals x, that forms sort of the lower bound of all my x values of this solid. But actually the upper bound of the x values is going to be a function of y, because the upper bound of my x values in the solid is going to be that parabolic cylinder. So for my lower bound, I'm going to use the plane z equals x to bound the values of x I'm allowed to use from below. And then for my upper bound, I'm going to use the formula x equals 4 minus y squared. Because it only depends on where the parabolic cylinder is. Okay, so now if I evaluate this triple integral, then it should give me the volume of that solid. So first, taking the antiderivative with respect to x is going to give me just x. And I'm going to evaluate that at 4 minus y squared and at z. So really, I can just write 4 minus y squared minus z. Okay. Now I take the antiderivative with respect to y. And so the antiderivative with respect to y is going to be 4y minus y cubed over 3 minus zy. And for y, I'm going to plug in the root of 4 minus z and the negative root of 4 minus z. So this here, my integrand of this, in terms of just y, since I'm taking the antiderivative with respect to y, I'm integrating with respect to y, in terms of just y, this is an even function, right? Because I've got the y squared, so that's even. And then I consider 4 and z to be just constants as long as I'm integrating with respect to y. So I've got an even integrand, and the bounds of my integral are negative and positive, the same number. And so that's going to be just double what I would get if I took the integral from 0 up to this square root of 4 minus z. So just using the even symmetry there. And that just simplifies things just a little bit. I can write 4 times the square root of 4 minus z minus 1/3 times 4 minus z to the power 3/2 minus z times the square root of 4 minus z dz. Oops. Okay, now I need to take this antiderivative, and I think it'd be nice to do a u sub, where u is just 4 minus z. And this isn't a really crazy u sub by any means. This is just gonna give me a negative and then I'll have 4 times the root of u minus 1/3 times u to the 3/2 minus 4 minus u times the root of u du. My new bounds are going to be 4 minus 0 up to 4 minus 4. Or I could just make this positive and then flip the bounds and then keep it 0 to 4. Right? Because if you change the sign of your integral, you can exchange the upper and lower bounds of integration. Okay. So having done this u sub, I'm going to simplify this even further because there's some like terms I can collect. Like, I've got a 4 root of u and a minus 4 root of u, so actually the roots of u go away there. And then I've got minus 1/3 u to the 3/2 power, and then plus u to the 3/2 power. So that's going to be 2/3 u to the 3/2 power. Check my work, did I do that right? think so. Let me know if I make any mistakes. And then this is going to be the same thing as, well, I can take the antiderivative, so this is going to be 4/3 times u to the 5/2 power times 2/5, evaluated at 4 and 0. So 8/15 times 32. And 8 times 32 would be 64, 256 over 15. And for some reason, I thought surely this volume would have like I thought it would be irrational.
Question, should it be, okay, so whenever we did the du sub, wouldn't it be negative that we have to pick up? This is dc negative equals du.
Yeah. Yeah, you're right. So,
Yeah, that's fine.
yeah, to answer your question, yes.
Yeah.
We put a negative sign here, and then I took it away. And I should probably just write out every step that I do so I can go back and point it out. But
Check the bounds.
yeah. This was negative, and then I had lower bound 4 and upper bound 0. You know, because if I plug in my previous bounds, whenever I had dz, this bound was 0 and 4. But if I plug in my lower bound 0, this would be 4 minus 0, so I'd have lower bound 4.
Oh.
And then I'd have 4 minus 4, so it would give me upper bound 0. But if I wanted to have, if I had 4 and 0, and I wanted it to be 0 and 4, I can exchange the upper and lower bounds of an integral, and then just swap the plus or minus sign. You're allowed to do that. And have I showed you guys the reason why you're allowed to do that? Did I explain that? No? Okay, so fundamental theorem of calculus. The fundamental theorem of calculus says if I have a definite integral from a to b of f of x dx, this is the antiderivative of f evaluated at b minus the same antiderivative evaluated at a, right? So what happens then if I have the integral of b to a of f of x dx? This would just be the antiderivative of f evaluated at a minus the antiderivative of f evaluated at b. And so that would just be the negative of this integral. So that's what I did, is I swapped the upper and lower bound, and then I changed the negative sign to a positive sign. But I did it just by erasing and rewriting it, so I don't have evidence to show you that's what I did. Okay. Like I said, I really thought that this volume would be irrational, and so I'm kind of surprised that my answer is not irrational. I really expected to pick up like a square root 2 or a square root 3. So let me double check my answer. No, that's actually it. Okay, so no mistakes. That's actually just a really... It's neat that that's a rational volume. Okay. Any questions about this example? And by the way, I just arbitrarily chose the order of integration dx, dy, dz. There's probably an easier way to do it. Like, I'm not for sure, but I think it would be easier if we did dz, dy, dx. But I don't have time to do it every way for triple integrals. In fact, for triple integrals, there are 6 different ways you could do the order of integration with rectangular coordinates. You could do dx, dy, dz, dx, dz, dy, dy dx dz, dy dz dy dx, and then dz dx dy, dz dy dx. And so there's 6 different ways you could do the order of integration. And so I would need 6 semesters to show you all the examples. Okay, and this is just really quick review. But a 2D scalar field, if anybody asks you what a 2D scalar field is, this is just a function with 2 input variables and 1 output variable. Okay, so like an example of a 2D scalar field is like population density. If I took a map of the United States and I overlaid an XY plane, then I could give you 2 input variables. And this time my inputs would be an X coordinate and a Y coordinate. And then the scalar field population density would give me 1 output variable. And that output variable would be the population density in terms of like number of people per square mile, right? And so if the coordinates I give you are, well, if you say that x is equal to 2 and y is equal to 3/4, then that is Chicago, and your population density is going to be large, right? If I gave you instead the coordinates x equals -4 and y equals 3, then that is the middle of Montana, and your population density is practically 0. Okay, so this is what I mean by a 2D scalar field, and it looks like my TV quit working, but maybe I can reboot it. Oh, TV. Okay. One thing I really like is these nighttime pictures, these satellite images. Cancel. And if you really want to, if you think you're good at geography, see how many of these little bright spots you can name. You know, like here's Dallas Fort Worth. There's Midland, Odessa, Lubbock, Amarillo. There is Albuquerque. And that's Denver, Colorado Springs, that's Phoenix, Tucson, Las Vegas, Salt Lake City. You know, just see how many of these cities you can name. But it's interesting to me that the bright spots are where there's a high population density, and the dark spots is where there's practically nobody, right? And so you look in Montana and there's practically nobody, but you look around Chicago and there's a lot of people. You know, so that's kind of a neat visual of what I mean by population density. You can think of that as a way to visualize that scalar field. Huh? Yeah. Yeah, exactly. Yeah. The urban areas, the cities are going to have a really high population density, and then the rural areas are going to have a lower population density, however you choose to measure that in practice. Okay. So that's one thing. A 3D scalar field then is going to be a function with 3 inputs, x, y, and z. A function with 3 input variables. And so in this class there's going to be x, y, and z inputs, and then 1 output variable. And so just some physical examples, really briefly, is if you have a 3-dimensional object that has different densities, you know, like you have like I don't know, like a giant metal sphere, but some parts of it have different alloys, like some parts of it have more copper, and some parts of it have more iron, and some parts of it have more uranium. Then certain parts with the more uranium are going to be more dense, and the parts with the more copper are going to be less dense, and etc. Likewise, if you have a big solid, it might not have uniform temperature throughout, right? Maybe you're heating part of your giant block of metal, and so it's going to be warmer on that side and cooler in other parts of the solid. And so you could have temperatures that even if you have the same solid, if you choose different x, y, z coordinates to describe your location inside the solid, you can have a different temperature. So that's an example of an output variable. In meteorology, you model, the entire weather system as being like, here's the ground, here's the top of what you would consider the practical atmosphere, right? Which doesn't really have a top. It's more gradual, but, you have to parameterize it with a z coordinate to talk about how tall your elevation is of the place you're talking about, and then, have some kind of north, south, east, west, x, y directions. And then you can talk about how the temperature changes. As you go up from the surface, temperatures generally get cooler. As you move around on the surface, temperatures change. You also care about atmospheric pressure, which would be another scalar field in 3D space. In the manufacture of solar cells, like you want to do the old-fashioned silicone crystalline photovoltaic cells, you start off with a big slab of silicone. And what they do is called doping, where on one side of your silicone object, your silicone slab, you hold against it a big mass of boron. And on the other side, you press against it a big mass of phosphorus. And then you heat it up to like a certain temperature where you don't want anything to melt, but you want to increase the rate of solid-solid diffusion. So that way you can get some boron migrating into your silicone crystal, and you can get some phosphorus migrating into your silicone crystal. And so at the end, when you are done, the side that was exposed to the boron is going to have the highest concentrations of boron, and the side exposed to the phosphorus is going to have the lowest concentration of boron, just because it takes some time for boron to diffuse, and the same for the phosphorus side. And so you could talk about the concentrations of boron as being a scalar field inside your three-dimensional silicone slab. You could talk about the concentration of phosphorus being a scalar field. The same thing happens with carbon steel. Like if you are making carbon steel, generally you make iron first, right, in your smelter, whatever you call it. In your foundry, you make iron, and then you dope it with carbon, I think using the same process. Well, I think there's a lot of different manufacturing techniques, but in one manufacturing techniques, you can dope iron with carbon by just smashing carbon next to the iron, heating it up so you don't want the iron to melt, you don't want the graphite to melt, but you just want to heat it up so that there's some solid-solid diffusion happening. So even in carbon steel, there's areas that have higher concentrations of carbon and areas that have higher concentrations of iron. I thought of unmixed lemonade this morning because sometimes I add like a lemonade packet, like the powder, to my water bottle. And if I don't mix it, then there's a higher concentration at the bottom of sugar, higher concentration of sugar, and there's lower concentrations at the top. So you can think of this as being a solid with an x and a y and a z coordinate, and there's different concentrations at different points. So just some physical examples of this. We can integrate 2D scalar fields using a double integral, right? So the region we're integrating would be like an area in the plane, but we can integrate using a double integral. If you wanted to integrate population density, what that would look like is you choose a region, a two-dimensional region, and then integrating would be basically counting up how many people live inside this region. So if my scalar field, if my integrand is describing population density, and I integrate that over this region, it gives me the total number of people living in the region. Okay. We can also integrate 3D scalar fields using a triple integral over a region in 3D space. So that means different things, right? If I took a triple integral of the density function, then the integral would give me the mass of the object. If I took an integral of the temperature of an object, that might give me something like the total thermal energy of the object. if I took an integral of probability density, then the integral would just give me total probability that an outcome lies in that region. If I took an integral of the concentration of boron, then that integral would give me the total amount of boron in that region of my solid. And then if I took the integral of the concentration of sugar in my unmixed lemonade, that would just give me the total amount of sugar, and so on, right? So these integrals, these triple integrals, have physical interpretations that we can assign to them. So let's see how many examples we can do. This first example is just like the one I gave where we were finding the volume, except now, if I take the triple integral of this, I would have to use the same bounds as before if I use the same order of integration, so I'd still have to use 0 to 4, negative root 4 minus z, and then z to 4 minus 1 squared. Okay, now, if I took this triple integral and I actually put a real integrand in there and not just the number 1, this triple integral would tell me the mass of the solid if the density of the solid were given by this scalar field function, right? And so what I'm trying to say in this problem is if you give me the x, the y, the z coordinates of the point you're talking about inside this solid, then I can tell you what the density is, right? And so if this is a mass density, it would be something like kilogram per meter cubed. So if I tell you the density in kilogram per meter cube is 1 plus the x coordinate squared plus the y coordinate squared plus the z coordinate squared, then obviously every point in the solid might have a different mass density. But if I take the integral of the density function over the whole 3D space, this integral is going to give me the total mass of that solid. Does that make sense? Okay. Again, a lot of times with these questions, I don't know how the math of solving the integral is going to turn out. And so on your exam next week, I might have a lot of questions that say just set up the integral, because I don't really know if it's going to be too long or too difficult or whatever. And so I don't know. I don't want to assign a problem that can't be solved. Ooh, I think I copied and pasted the same thing. So let's move on. Yeah, you're right. Okay, center of mass. So let's talk about center of mass then. The center of mass for a 3D solid, I would say has coordinates x bar, y bar, z bar. And then I'll give you the formulas for x bar, y bar, and z bar. Of x times and then of course y bar is going to be the triple integral over your region of y times your function. And then the z bar is going to be the triple integral with a z times your density function. Okay. So just to be super clear about what I mean here, the center of mass of a 3D solid is going to have three-dimensional coordinates: an x-coordinate, a y-coordinate, and a z-coordinate. If you memorize one of these formulas, you've memorized them all. They're really easy to remember, symmetric, right? So x bar is the triple integral. So here you would have to find the lower bound and the upper bound that describes your solid in 3D space. And the integrand is going to be your density function. F is the function that describes the density of the solid. But then I'm also going to multiply by an extra little x as a factor. That tells me how far this mass that I'm adding up, all the little densities times dv's are little mass. How far away are these from the YZ plane, which is the moment, I guess you could say, in the x direction. And so all these formulas are the same. If you memorize one, you memorized them all. But that's how you would find the center of mass. I'm not going to give you any problems that ask you about moment of inertia. I think center of mass is as far as I want to go in that direction. Let's see if we can evaluate this triple integral before in the next 10 minutes. It's a speed challenge. Okay. So to begin, we're going to sketch this region in 3D space so that we can have a feel for what we're actually integrating over. And so that is, of course, easier said than done. The first step is drawing an XYZ space. And what I know about this is that Y is allowed to be anywhere between 0 and 9. X can be anything between 0 and y divided by 3. And z can be anything between 0 and the square root of y squared minus 9x squared. So everything is happening, it looks like, in what we would call the first octant. I say octant because, in the xy plane we had quadrants, the first, second, third, fourth quadrant that we labeled counterclockwise. In three-dimensional coordinates, these planes create 8 different regions of 3D space about the origin. I can honestly, I don't know how you number the rest of the octants. I don't know how you number them 1 through 8, but I do know that the first octant has all positive values of x, y, and z. And so I say that this whole solid is going to be in the first octant because I have that y has to be greater than 0, x is greater than 0, and z is greater than 0 by looking at my lower bounds of my integrals. Okay, so all of this is happening kind of in this region of space, in the first octant. So y can't be larger than 9, and so at some point on my y-axis there's a point 9, and I can't go past that. For my upper bound of x, I can write x equals y over 3, or I could write y is equal to 3x. And I'll try to draw the line y is equal to 3x in the xy plane, and it's kind of going across like that. It's really hard to draw this in three-dimensional space, right? Because it kind of looks like this is going up, but it's not. It's going back into the xy plane. This is the line y equals 3x. And then for my z, I can set z equal to the square root of y squared minus 9x squared to try to get a feel for how z works. And this gives me z squared is equal to, well, let me write 9x squared minus y squared plus z squared equals 0. If I rearrange that enough. And this is true if x, y, and z are all equal to 0, so I know that this belongs to the origin, or the origin belongs to that set. Yeah?
Y equals 3x. Be centered on 3.
Oh, you're right. Sorry. That's a great point. Y equals 3x. So, that means this point, 390, that actually should belong to the line y equals 3x. Okay. That's a really good point. A very good catch. Yeah, it's hard to orient yourself, but yeah, I think that looks correct now. Now that you corrected me, very good. So, so this is not a sphere and it's not an ellipse, because I have this negative y squared. That's going to make this some kind of hyperboloid. Or maybe not. I'm having a hard time today. I need to graph this so I know what it looks like. So let's try out graphing this thing. And technically, on an exam, if I ask you to evaluate this triple integral, I'm not going to ask you to sketch something in 3D space. You're only going to have to work out the problem, not actually sketch it. But I think it's nice to sketch things. I think it's nice to actually know what we're talking about, the region we're talking about. So, 9x squared minus y squared. Okay, so this is, it's a cone. It's a cone, which is kind of a limiting case of a hyperboloid. But, so let me put in the other equations, like y equals 3x. And I know I'm in the first quadrant, so I know I'm over here. And how else is this bounded? Oh, y can't be greater than 9, so let me type in y equals 9 in there. Okay. So the volume I'm looking for is in the first quadrant, so it's in that direction. It's in this part. And it's got, I really don't even need that, but it's like a slice of that cone. Okay. So if I had to sketch it, then actually no, this should be vertical. That should be a linear thing, and then this should be rounded to that. Okay. Then there's going to be a distance of 3 here, and I think a distance of, what is it? Is it 9? Yeah, 9 here, but it's a bizarre shape. Okay. So the scalar field that we're integrating, I don't know if you see it, But before the dz, dx, dy, before all of my order of integration stuff, I've got a little z there. And so the scalar field that we're integrating is just the function z. So it's going to have positive values because we're in the first octant, and the value of my scalar field is increasing as we get up towards the top of this solid. So this is going to be the highest values of my scalar field, and these would be approaching 0 down here at the base. Okay, if I were going to take the antiderivative of z, that would just be z squared over 2. And so this is going to be this. And I'm evaluating z squared at upper bound square root y squared minus 9x squared and 0 dx dy. And then whenever I plug these in, obviously the 0 is just going to be 0, so I don't really care about the lower bound so much. If I plug in the upper bound, I just get rid of the square root because I'm squaring it, right? So this is just going to be so it's going to be y squared minus 9x squared. Oops, that's supposed to be a y. Y squared minus 9x squared. So integral from 0 to 9. And then if I take the antiderivative of that stuff with respect to x, it's going to give me xy squared minus 3x cubed. Now I would evaluate that at y over 3 and 0. And then whenever I plug in x equals y over 3, I don't have to worry about the 0 case, because if x equals 0, then the whole thing is 0. So I only really care about the upper bound here. And so if x is y over 3, then this is going to be y cubed over 3 minus 1 over 9 times y cubed, right? So a third minus a ninth is going to be 2 ninths. So I'll go ahead and put that out front. And then all I have to worry about is the antiderivative of y cubed, which is going to give me a 1 over 4. And then the antiderivative will be y to the 4th, and evaluate it at that 0 and 9. And so 9 to the 4th power is really a large number. And then these 2's will cancel, and so it'll be times 1/4 times 1 over 9. So this will be like 9 to the 3rd power over 4. And 9 to the 3rd power would be 81 times 9, which is 729. Okay. dz dx dy. There we go. Okay, so you just have to type in the words. And that was our answer, right? 729 over 4. Perfect.